Dear student, I hope that all of you are well, and we will be discussing or we will be learning about the chapter integral transforms. And now, what is integral transform? So, integral transform is a mathematical tool with which we can uh, easily solve different kind of boundary value problems, and we will learn in details in our next classes, and we will cover this chapter using different or several or number of classes. This is the first class, and in this class we will concentrate or we will have a look on the Fourier analysis first. And now, so we are now are here to just recapitulate about the Fourier analysis that we have learned in our uh, previous classes, that is in case of graduation levels, etc. So now let us start, or let us go to the uh, Fourier analysis. So now, although the topic is written as Fourier transform, as I already discussed that using integral transform, we can easily solve very, very hard kind of problems, boundary problems, using integral transform. And there are several kind of integral transform. Number one is the Fourier transform. Number two is Laplace transform, Henkel transform, Nailing transform, etc., which we will learn. And in our syllabus, we have to study only the Fourier transform as well as the Laplace transform. So we will concentrate on these two transforms. But before doing that, we just have a brief look on the Fourier analysis. As you know, that Fourier analysis is a very strong and powerful tool, or powerful mathematical tools, which is applied in not only in the diverse field of physics, but also in case of acoustics, optics, and electricity, as well as other fields other fields like astronomy, electronics, engineering, etc. And this Fourier analysis was developed by the mathematician Fourier, Bernoulli, and Euler. And using Fourier analysis, we know that this can be applied to decompose or to express a function which is composed of sine or cosine series, cosine term series. So, a function which is composed of sine or cosine series, you can divide or decompose that function into a combination of sine and cosine series. For example, in case of oscillations, you can do it, and conversely, you can also do, or also you can find out the resultant of a number of sine and cosine waves, oscillations, etc., or number of sine or cosine functions to a resultant function. So this is why we frequently use Fourier analysis. And now, therefore, it is important in case of mathematics, not only mathematics, as I told earlier, that it is also applied in case of physics or astronomy or engineering sciences, etc. And we already learned about it, and now just we focus on some topics on it. Number one is first. So before doing that, we have to the knowledge of Fourier series. What is Fourier series? So the Fourier series can be defined in such a way that if you have a function which is single valued, so this function is fx, and this function is defined in the interval minus pi to plus pi. This is a closed interval, and your function fx is defined in this closed interval. Then, according to Fourier theorem, you know that these fx can be expressed in a series of the resultant of sine and cosine terms or cosine functions as represented here. That is, fx is equal to a 0 by 2, then plus n is equal to 1 to infinity n cos nx plus n is equal to 1 to infinity bn sin nx. In this case, you see here this term, this an and this bn are the sine and cosine constants or coefficients, and a0 is the constant, and the right hand side is the Fourier series expansion of the function fx, and the functions the constants a0, then a1, and then bn can be expressed as given below. Here is the a0. This is given by 1 by pi minus pi 2 plus pi fx dx, and then uh, an is equal to 1 by pi minus pi 2 plus pi fx cos nx dx, and bn is equal to 1 by pi minus pi 2 plus pi fx sin nx dx. And remember that the right hand side of this equation, this is here, fx is equal to this plus this plus this. This is the Fourier series expansion of the function fx. And as I already stated that these the coefficients an and bn are respectively called the cosine and sine coefficients. And so now to express this function, in in the combination of sine or cosine series, that is to express a function in Fourier series, we need to have follow the following conditions. Number one is here, the function fx should be bounded. The function or fx which we are interested, which we have to express in terms of sine and cosine series, that is the function is fx, that should be bounded. That means it should satisfy the condition mod fx less than or equal to c, where c is a constant and for all values of x. So it should be bounded. This is the number one condition. Number two condition is that the function fx should be single value. That means for a certain value of x. So if you consider that the function is fx, so it is a function, or it is it's depend on the variable x. Then for a certain value of x, the function should have a single value, not multiple value. Okay, if it has multiple values for a certain value of x, then it could not be expressed in Fourier series. For example, is here. See here, this is a graph in which fx is plotted against x. So here, see this for the point x1, it has a certain value, it has a single value. But in case of at the point x2, it has, this is number one, this is number two, and this is number three. That means there are three values. So that means fx has multiple values at the point x2. So it has not single value. For and similarly in case of x3, here are two values. That means multiple values of fx for the value x2 and x3. That means at the point x2 and x3, fx cannot be expressed in terms of Fourier series. And the number three, the condition number three is here. The function can have only a finite number of extrema or extrema. That means maxima or minima for a certain value of x. So if it has infinite number of extrema, that means maximum or minima, then it is not possible to express the function fx in terms of sine and cosine series, that is in Fourier series. So for example, see here in between the points x2 and x1, that is x2 and x1, see here there is a number of extrema, that is maxima and minima. So if it has the maxima and the minima has a large number of values, that means within 2 points, if fx has a large number of maxima and minima, then it cannot be expressed. So in this case, it cannot be expressed. But in case of x2 and x3, see here the maxima and minima are finite. So in that case, it can be expressed in terms of Fourier series. And number 4 condition is here, the function must be piecewise continuous or piecewise continuous. At least it should be piecewise continuous. If the function fx is continuous or at least piecewise continuous, then it can be expressed in terms of Fourier series. See this figure here, from the point 0 to x1, or from the point x2 to say let it is suppose it is x3, or x1 to x2, this is there, that means this one, and that means for the first case 0 to x1, that is this one. In this case the function is continuous, and in between x1 to x2 this point, this is also continuous, and from x2 to say it is x3, this point is, so this is also continuous. So it is piecewise continuous. So to express a function fx in Fourier series, that function should be continuous. At least it should be piecewise continuous, and if that happens, then it can be expressed in terms of Fourier series. Now, Fourier sine and cosine series. So first we need to have a knowledge about the even function, and I hope that you all know what is an even function. Yeah, so the even function is defined as if a function fx, you have given a function, you have provided function fx, and if the variable x changes its sign, and then if the function have the same, if the function has the same value, the function does not alter, then the function is said to be an even function. That means the function fx is said to be an even function if fx, f of minus x is equal to fx in the interval or in the range. This is the range minus pi to x, pi minus pi less than x less than pi. That means in the closed interval minus pi to plus pi. Then the Fourier coefficients are as follows. Then the Fourier coefficients are, can be written as, and we know that the first this condition a0 can be written as 1 by pi minus pi to plus pi fx dx, and that can also be written as this limit is, can be expressed as 0 to pi with multiplication of 2, that is 2 by pi 0 to pi fx dx, and then an is equal to 1 by pi minus pi to plus pi fx plus nx dx. That can also be written in this fashion: 2 by pi 0 to pi fx cos nx dx, and bn is equal to 1 by pi minus pi to plus pi fx sin nx, and that is equal to 2 by pi 0 to pi fx sin nx dx. Now, interesting thing is there here that if fx is an even function, in that case bn, this bn, that means this bn becomes 0, and that can also be found from here. So here for even function bn is equal to 0, it has been proved here. Let fx is equal to cos x. If, because you know that in case of if x changes its sign, that means cos of minus x, that is equal to cos x. That means cos x is an even function. So in that case, we are here to find out the value of bn. That is equal to, we already write it in this fashion, that 2 by pi is equal to pi, then sin nx, it was in the definition, and then cos x dx. That is there 1 by pi, you can write this 2 sin x, 2 sin nx cos x. That is 2 sin a sin b. That can also be written as sin a plus b, and then sin a minus b. That is here 0 to pi sin n plus 1 dx, then plus 0 to pi sin n minus 1 dx. After integration, after integration, you will have 1 by pi. From here, sin means that this will give you cos n plus 1x by n plus 1, and integration of sin actually give you a negative sign. So here will be a negative sign. Here will be a negative sign. So plus then cos n minus 1 by n minus 1 into x. Now just use the value of 0 here, since and pi. Using these limits, you can easily understand that the value bn is equal to 0. So in that case, fx should be a0 by 2, then cos sum over an cos nx. That is the cosine series will be there. Now go to the here, come here, and now what function? And in case of what function, you know that if x changes its sign, the function also changes its sign. That means what function is defined in this way, that f of minus x is equal to minus fx, and which is also, and this is true for the range minus pi less than x less than pi. And then the Fourier coefficients are as already written in the first case, that is in this case you see here, that is also written here that a0 is equal to 1 by pi minus pi to plus pi fx cos x dx, and this value should be, in that case a0 an a0 becomes 0, that is a0 vanishes in this case, and also an, that is the cosine coefficient, that is 1 by pi minus pi to plus pi fx cos nx dx, that is also 0, and bn is given by 1 by pi minus pi to plus pi fx sin nx dx, that is 2 by pi 0 to pi fx sin x dx. So in that case only bn will exist. However, a0 or an vanishes in this case, and that is also here. It is for what function an is equal to 0, you can take as the function as sin x, and using this sin x, you would just, it is your homework, you would just write it in this function that fx is equal to sin x, and compute it, and you will easily you can compute it. You can easily find that the value of a0 should be 0. So I am not shown here. I have not shown here, but only the value of I have shown here only the value of an is equal to 0 in these calculations here. So in this case, right, let us consider that the function is sin x, which is an odd function, right? Because you know that sin of minus x is equal to minus sin x. Now using this, you just write here an is equal to 2 by pi. You know the definition, 0 to pi is cos nx sin x dx. And that can also be written in this fashion, that sine of n plus x minus sine of n minus x, because this is the 2 cos x sin x. That can also be written in this fashion. And after integration, this term will give you cos n plus 1 by n plus 1 into x, then cos n minus n, because this is a negative sign, and sine integration of sin x will give you another negative sign, that will give you positive sign. So this, and just use the value of y and 0, that is done here, and a n finally becomes 0. So in case of odd function, a0 and an both both become 0. So in that case, fx can be expressed only in the series of, only in the combination of sin x. So that is n is equal to 1 to infinity bn sin x. This is for odd function. Now example of even function, this kind of function, that is x square cos x, x to the 4, sec x, are the examples of even functions. And in case of even functions, graphically an even function is symmetrical about the y-axis. So it is, in this figure, this is the representation of an even function that is here, and it is plotted against x. And this you can see here, in this direction x is positive and this direction x is negative. So this is symmetrical about the y-axis. This is the y-axis. So these values and these values are equal. So in that case, for these values and for these values, fx has the identical value. So that means for the even function, the function is symmetrical about the y-axis. And now the example of an odd function, x gives sin x, tan x, x to the 5, etc. are examples of odd function. And this is the representation of an odd function against x. And in case of odd function, the function is symmetrical about the origin, that is here. See here, this is here. Now another important form term, that is complex form of Fourier series. So we need to have the complex form of the Fourier series, and we know that the Fourier series fx of a function, fx can be expressed in this fashion, that is 0 by 2, then plus n is equal to 1 to infinity an cos nx plus bn sin nx. And that can also be written as a0 by 2, then n is equal to 1 to infinity an. This n is here, you know that cos nx can be written in this fashion, e to the inx plus e to the minus inx by 2. And then plus somewhat be just separate these two terms, n is equal to 1 to infinity bn, and you can write sin x nx as this should be sin nx. So be careful, this should be sin nx. Sin x nx can be written as e to the power inx minus e to the minus inx by 2. The next one is here, a0 by 2, then plus n is equal to 1 to infinity, and just look at here this term and from this term and this term a e to the inx. So e to the inx is a common term, so from here only an is here, and from this term this is multiplying by this with this term. So e to the inx is here, there is n, but this, see here it is 2y. So multiply the denominator and numerator by I. So that will give you minus 2 here, and here I into this, another I into this here. So here minus 2 is in the denominator. Okay. So now that will give you minus I, from here I, then bn. This bn is here by 2. So from here an minus I bn by 2 to the inx. And the next one is here, that is in this case the common term will be to the minus inx. That is here, and from here an is here, and from here you see here I is here, and minus 2 is here. So minus 2 and this minus will give you plus sign, then I bn by 2. So this is, so from here, from this line we can get this line, and after that fx is equal to, you can write this expression as n is equal to minus n into plus cn e to the inx. Just look at here, where c0 is equal to, so c0 is equal to, so when n is equal to 0, then it will give you c0 into 1, that means c0, only c0, and c0 is equal to a0 by 2. If you write c0 is equal to 0 by 2, then this you can write fx in this way. Okay, no problem. And with this cn, so now we have to define cn. Cn is equal to, since n has both negative and positive values. So Cn is equal to half this value an minus Ipn, that is here, and C minus n for n is negative number. C minus n that will equal to an plus Ipn by 2, that is here. So now just you use the values of different values of n starting from minus infinity plus infinity, that will provide you this. And if you use the value of n is equal to 0, then that will give you a 0 by 2, that is this value. So we can write this expression in this fashion. So fx is equal to n is minus infinity plus infinity Cn e to the inx, and this is the complex form of the Fourier series, and C0, Cn, and Cn are called the complex coefficients of Fourier series. Now, just multiplying this equation by the term e to the minus inx, and then integrate with respect to x in the limit minus pi to plus pi. So what that will provide you? That will provide you fx, that is here e to the minus imx and e to the minus pi to plus pi dx, that is equal to here minus sum over n is equal to minus into plus infinity, that is written here. Then Cn is here, integration minus pi to plus pi e to the power inx, that is here, e to the power inx, and then multiplied by e to the power minus inx, that will give you e to the power in minus n x dx. That can be written as sum over minus n to plus Cn, then 2 pi delta mn, where delta mn is the Dirac delta function. Okay, this is the Dirac delta function, and delta mn is equal to 1 when m is equal to m and m both are equal, then delta m is equal to 1, or if m and n are not identical, then delta m is equal to 0, and that means from here you can finally write 2 pi into Cn. Okay, so 2 pi into Cn, so Cn is equal to, from here you can write Cn is equal to 1 by 2 pi minus pi to plus pi fx to the minus inx dx. So in this way you can calculate the value of Cn. If you want to know the value of Cn, then you can also find out the value of minus Cn. So no problem with this. And minus Cn is here, 1 by 2 pi minus pi to plus pi fx to the power inx, just replace this n by minus n. So that is here e to the inx dx. And C0 is equal to 1 by 2 pi, just use n is equal to 0 in this expression. That will give provide you 1 by 2 pi minus pi to plus pi fx dx, that is equal to 0 by 2. So all the values of C0, Cn, C minus n can be computed by the knowledge of fx. Okay. Now here is so this is the preliminary topics, that means the brief recapitulation of Fourier series that we have learned in this, or just we have discussed in this class. So this is the end of this class. You need to have just have a look on this, and after this we will start, or we will begin our next class with Fourier transform. Okay.